In this video, we are going to start to define probability and probability event spaces. We're going to use probability notation for the first time. So what probability is a measure that's associated to how certain we are of the outcomes of a particular experiment or activity. Now, the probability is a number between 0 and 1, 0 being that it never happens and 1 being it always happens. And then a 0.5 means that the outcome is equally likely to happen or not happen. And the probability of any outcome is the long-term relative frequency of that outcome. So we're going to be planning experiments with our probabilities, and then we're going to count how often this outcome happens, and that will give us our probability. If the result is not predetermined, then the experiment is said to be a chance experiment, such as flipping a coin. When you flip a coin, you don't know if it's going to be a head or a tail. The chance of a head and the chance of a tail of a fair coin is a 50-50, or in other words, 0.5 as a probability. But we don't know what the outcome is prior to flipping the coin. The result of an experiment is called the outcome. The sample space of an experiment is the set of all possible outcomes. So if you are flipping a coin, a fair coin, you have a choice between a head and a tail, and that would be the possible outcomes for one flip of a coin. Uppercase letter S is used to denote the sample space, and an event is any combination of outcomes. Uppercase A's and B's usually represent events. So for an example, if you are rolling a fair die, a 6-sided die, the event A might be rolling a 3 or less. And the way that you would write this is the probability of A happening would be P of A. P of A, P with parentheses and then the capital A, where A represents rolling a 3 or less. Equally likely means that each outcome in the experiment will occur with equal probability. So if you flip a coin, that's a fair coin. That means that it's not heavily weighted on one side or the other, that you're equally as likely as to get a head as a tail. If you toss a fair 6-sided die, the sample space are the numbers 1 through 6, and each face is equally likely to occur on each roll of the die. Now, the law of large numbers, this says that basically what we expect to happen will eventually happen if we do it a bunch of times. What does that mean by that? So if we roll a die and I expect a 1 to show up 1 in 6 times, so in other words, my probability of rolling a 1 is 1 over 6, 1 divided by 6. Now I roll the die and the first time I don't get a 1. Well, if I keep rolling the die and I make note of how many times the number 1 comes up out of the number of rolls, eventually, by the law of large numbers, I am going to get something that's equivalent to 1 over 6, eventually. Now, it's important to realize in some situations the outcomes are not equally likely. The coin or the die may be biased or unfair, so that's why we talked about a fair coin. In other words, one side of the coin is not heavier than the other. When order matters, then rolling a 6-sided die and getting a 2 and then a 3 is different than rolling a 6-sided die and getting a 3 then a 2. When order doesn't matter, rolling a fair 6-sided die and getting a 2 and a 3 is the same as getting a 3 then a 2. And we're going to talk more about this later in the chapter when we talk about the importance of order and order not mattering. There are 3 ways to represent the sample space. One is just to list them. One is to create a tree diagram, and I'll show you what that looks like. And one is to create a Venn diagram, and I'll show you what that looks like. So if you wanted to list the possible outcomes of flipping a fair coin twice, then what you'll get is a head then a head then a tail then a head, and then a tail and a tail, where order matters. That's just the list. If I want to do a tree diagram to represent this, I could get a head, which is a 1 in 2 chance of getting a head, and then I can get a tail, which is 1 in 2 chance of getting a tail. In other words, 0.5 probability. And then if I get a head, I could then get a head, so this is where I get head, so this is head. And then I could get a head, then a tail, And so this is where I get a head, then a tail. And then I could go down this tree, this branch, and get a tail, then head, and then a tail, then tail. So going down this would be a tail, then a head, and then going down this other branch would be a tail, then a tail. Now notice I have the same sample space here as I have on this tree diagram. And what I did is I went down each branch, head, then head, head, then tail, tail, then head, tail, then tail. Now doing a Venn diagram of a tossing a coin or flipping a coin, a fair coin twice, is I could get a tail then head, which is different than the head then tail. The overlap would be that you get a tail tail, and then out here would be a head head. So this also could represent the sample space. Now I personally would not do a Venn diagram for a coin toss. I might do something like this, or I might just list them out. I'm unlikely to do a Venn diagram for a flipping of a coin or rolling of a die. I will use it for other things, but probably not that one. So to calculate the probability of some event A happening is going to be the number of outcomes in the event A and then the number of possible outcomes in the sample space. Which is why when you roll a dice and say I wanted to say A was the number 1, there's only one way to get a number 1, and there are 6 possible outcomes when you roll a fair-sided die. Now there are 2 different things that we need to talk about, which is theoretical probability, and that's this. This is theoretical probability. And then that's based on the mathematical principles and assumptions and known properties of the system that we are looking at. So in other words, rolling the die. It's determined by dividing the number of favorable outcomes by the total number of possible outcomes, which is this. Theoretical probability is the prediction or the likelihood of an event occurring, assuming the ideal conditions, in other words, fair, without any empirical data or observation. The experiment would be taking note of how many times I roll a 1 and counting it and then rolling it however many times. So say I roll my dice and I get, the first time I roll, I get a 1, and then I get a 2, and then I get a 3, and then I get a 1, and then I get a 6, and then I get a 7. Not a 7, I can't get 7. I just like the number 7. So then I get a 4, and I'm going to pay attention. I'm going to do it one more time, and I get a 2. Now, this is the experiment. I rolled it. So my probability of A by my experiment is, again, I'm chasing a 1. I rolled it, let me see, 1, 2, 3, 4, 5, 6, 7 times. And I see 2 show up 1 time, so I have 2 over 7. And then if I go back to the law of large numbers, if I roll this 100 times, I'm going to get closer to that number 1 out of 6. I roll it 1,000 times, I'm going to get even closer. So that's what the law of large numbers is that eventually my experiment should approach or become as close to as possible the theoretical probability. So let's take an example. If you're rolling a 6-sided die once as an experiment, the sample space would be 1, 2, 3, 4, 5, 6, which are all the possible outcomes of rolling a 6-sided die. Rolling 2 is the outcome. So if A is rolling a 3, then P of A is 1 out of 6. The probability of A happening is a theoretical probability, but if you roll a 2, then the probability of rolling a 3 was actually 0 out of 6. And this is the empirical or observed probability or experimental probability because you didn't actually roll a 3, and that's just out of 1 time. Now, what would be the sample space if you rolled a fair-sided die twice when order does not matter? And then we'll also talk about when it does matter. If A represents rolling a 3 twice, what's the probability of an A? So if order does not matter, then rolling a 1, let me see if this is going to work, 1 and then a 1, and that is the same as rolling a 1 then a 1. So then rolling a 1 then a 2, rolling a 1 then a 3, rolling a 3, or excuse me, I'm going to do all of the possibilities of rolling a 1 first. So 1 and 1, 1, 1, 2, 1, 3, 1, 4, then a 1 and a 5, then 1 and a 6. And then I'm going to do it for 2. So then if I roll a 2, now assuming order doesn't matter, a 2 and a 1 is the same as a 1 and a 2. So I'd have 2 comma 1, which is the same as that. So then I would do 2 comma 3, or 2, 3. So it's not 23, it's 2, then 3. And then I'd have 2, 4, 2, 5, 2, then a 6. And then I'd be exhausted my 2's. So then I'd have my 3's. So 1 and 3 is the same thing as 3 and 1. And then I'd have 2 and 3, which is the same thing as 3 and 2. So then I have a 3, and then a 4, then a 3, then a 5, then a 3, then a 6. So I've exhausted my 3's. Then I'd have 3, so I'd be in 4, so 4 and 1, so 2 and 4. So the next one is 4 and 5, then a 4 and 6. And then I would have my 5, so then I'd have a 5, 5, then a 5, 6. And then the last one would be just 6, 6. So I'd count and I'd say I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible outcomes when order doesn't matter. So a 1 and a 2 is a 2, then a 1. And then if I have a 3 twice, did I miss something? Oh, I did miss. I did miss the 3 3's. I missed the 2 2's. Bad on me. So I'm going to add my 2 2, and I need to add my 3 3. I also need to add my 4 4. I need to add my 5. I got my 5 5, and I got my 6 6. So now let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So my sample space size is 21, and the chance of getting a 3 3 is just 1 out of 21. Now, let's talk about if order does matter. So if order does matter, then you have to pay attention to the sample space. So a 1 then a 1 is different than a 2 then a 1 is different than a 1 then a 2. So if you are rolling a 6-sided die and order does matter, there are 6 possible outcomes for the first die, and there are 6 possible outcomes for the second die. And so my sample space would be 36. So if order matters, and I'm rolling 3 and then a 3, that would be, if I did all of it out, it would be 2 out of 36. So pay attention if order matters or order does not matter. Let's talk about the or and the and event. So with an or, that means this or this could happen. So if we let A equal this and B equal this, and A or B is the combination, notice that we don't write 4 and 5 twice. So basically what you do with an or statement is you add everything you have in A and you have everything you have in B, and then you take off any overlap. So if you have the probability of A or B, it's going to be the probability of A happening plus the probability of B happening minus any overlap, and we call that the and statement. So notationally, what this is saying is probability of A happening plus the probability of B happening, and then this probability of A and this U, upside down U, is intersection or and. So that's the pulling off any overlap of the two sets. And that's what we did here. We said, okay, we're not going to write 4 and 5 twice, right? So I have 1, 2, 3, 4, 5. I'm going to add to it 4, 5, 6, 7, 8. And then you'd notice if I were to have listed out the probability, or if I would have just listed out A and B, so A union B, without pulling off any overlap, I'd have 1, 2, 3, 4, 5, 4, 5, 6, 7, and 8. Now, if I then pull off that intersection, and the intersection is a 4 and a 5, if I pull those two off, then I actually have a nice union where I don't have a repeats. And so I have 1, 2, 3, 4, 5, 6, 7, 8. So the overlap was 4, 6. And notice I pulled off just the overlap, which meant I pulled off one of that set that was repeated. Now the and statement is this and this has to happen, which means that I'm really looking for where I have overlap of the two. So that's my and statement, and this is the notation, the probability of A union, and that should be a B. of A intersect B. This is the and. And complement is the not in. So when we see complement, it's usually like an A has a prime, or might have probability of not in A. So P prime of A. So what we know is that if we take all of the probabilities of A and all of the probabilities of not A, that it will always add up to 1. So we add those two together and add them up, we're going to get 1. So if I have the sample space S, which is 1 through 6, and I have the sample space A, which is 1 through 4, then what's not in A is 5 and 6. So the probability of A is 4 out of 6. The probability of not A is 1 minus the 4 out of 6, which is 2 out of 6, which is what we have right there. So as in this example, we have a bag. There are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, and 6. The green marbles are marked with the numbers 1, 2, 3, 4. R represents a red marble. G is a green marble. O is an odd marble. So the sample space would red 1, 2, 3, 4, 5, 6. Green 1, 2, 3, 4. 1, 2, 3, 4. So then if I wanted to know what is the probability that it's green and so I'm looking for the overlap, and it's odd. So I know my sample space, if I list all these out, is 10 possible outcomes. And if I want a green one and an odd number, then the only one that is green and odd is G1 and then G3. So in this case, this is just going to be 2 out of 10, or in other words, 1 out of 5. Now, I want to know what is the probability of green or odd. So I'm going to do the probability of green. So the probability of green is going to be 4 out of 10. The probability of odd is going to be, well, my odd is red 1, red 3, red 5, green 1, and green 3. So the probability of odd is 5 out of 10. So the probability of green or, so this is a union of odd, is going to be the probability of green plus the probability of odd. And then I'm going to subtract off any intersection that I have, which is the probability of green and odd, which we know from here is 2 out of 5 or 1/5. So my green is going to be, probability of green is 4 out of 10, plus my probability of odd is 5 out of 10. I'm going to subtract off that overlap, which is 2 out of 10 because I'm counting it twice. And so I end up with 7 out of 10, which is the probability of getting a green one or an odd one. Here is a standard deck of cards. Most of the homework questions will show you the standard deck of cards. If not, then here's what it looks like. So a standard deck of cards, we have, I always wanted to call these dog feet when I was a kid. So we have the clovers, we have the spades, we have the hearts, we have the diamonds. And so you can see we go from ace, which could represent 1, 1 through 10, and then we get in the jack, queen, king for each one of them. What is the probability of not drawing a face card in a standard deck of 52 cards? And so the probability of not getting the face card is going to be, well, I'm going to do the probability of F, where F represents face card. And I can see that I have 3 in each one of these. So in other words, I have 12 out of 52. So then the probability of not a face card is going to be 1 minus the probability of a face card. And so this is going to be 1, and I have 12 out of 52. So that is 40 out of 52. So that's a probability of drawing not face card. Okay, so then I'm going to look for what is the probability of getting a 5 or less. Well, I have, for the first set, I have 5, I have 10, 15, I have 16 cards. So the probability of, I'm going to do B, where B is a 5 or less, is going to be equal to, what did I say, 20 out of 52? And of course, if I can reduce, I will. So I have 10 out of 26, which I guess I could continue to reduce. That's 5 out of 13. So 5 out of 13. And I actually could have done this a lot faster, is because I know that each one of them, have 5, and then there's 13 in each suit. So 5 out of 13 is what it reduces to. Conditional probability. So what conditional probability is? The probability of A given that B has already happened. And so this is probability of A given that B has already happened. And I kind of think of this as like a division, right? So this almost looks like a division. So what it is the probability of A given B is a probability of A and B happening given that B has already happened. So that's why I said this is kind of like a division. This is how I remind myself. It's A and B, the A intersect B, divided by the probability of B already happening. So here's an example. In a bag, there are 6 red marbles and 4 green marbles. The marbles are marked 1 through 6. So this is the same kind of thing. SS10 outcomes. Was the probability of green given that given that you've already chosen an odd one? So we know that this is going to be equal to the probability of green intersect the odd. Now we know the probability out and then divided by the probability of the odd one. So we already know the probability of the green given the odd, which we did up above, but we can do it again. So it's 1, 2. So the probability of green and odd is 2 out of 10. And then the probability of odds, well, I have 1, 2, 3, 4, 5. So I have 5 out of 10. And so this becomes 2 out of 10 multiplied by the reciprocal of that bottom fraction, the denominator fraction. So that's 10 out of 5. And so my answer is 2 out of 5. And that's my probability of giving that you're choosing a green one given that you've already chosen an odd one. Now here's a refresher of some symbols that you might need. So here's the greater than, which these are the words you would be looking for. Greater than or equal to, these would be the words that you would be looking for to translate into that symbol. Less than and less than or equal to. If X is an outcome, an event, and A is some value, then sometimes the way that we may do this is a probability of X not more than A would be wrote as probability of X less than or equal to A. So you might see this on the homework. Here's some notation, and that's it for this video.